Alright, we are looking at graphs of exponential functions. So the most basic form of an exponential graph is where our function is written like this: y equals b to the power of x, and this b is just any positive number greater than 1. So here's a couple of examples. We've got y equals 2 to the x and y equals 10 to the x. So let's have a look at how we get the shape graph that we do. So starting with an x value of -2 here, our y value will be 2 to the power of -2. So 2 to the -2 we know is the same as 1 over 2 to the power of +2, or 1 over 4, or 0.25. And so here our scale is 0, 1, 2, 3, 4, 5, etc. And so 0.25, or 1/4, is just down here, just a little bit above the x-axis. If we take an x value of -1, then that's going to be 2 to the -1 for our y value, which is 1 over 2, 1/2, or 0.5, so just a little bit higher. For an x value of 0, so right on the y-axis, then we've got 2 to the power of 0, which is 1. And so we have that value there. And so if we keep going with increasing values of x as we've got it there, 2 to the power of 1 is 2. So here, 2 to the power of 2, which is 4. Okay, so for an x value of 2, our y value is 4. For an x value of 3, our y value will be 2 to the power of 3, which is 8. So that's 3. And up here, our y value is 8. For an x value of 4, then that's going to be 2 to the power of 4, which is 16. And so we're up here. And so you can see the shape of our graph. It's growing slowly at first, but then quite rapidly as our x values progressively increase. And you can imagine if we're an x value of 5, then our y value will be quite up here, which will be 2 to the power of 5, or 32. And so for each successive x value, our y value is being doubled because of the 2 as our base. Jump over here for a base value of 10. Our y values will be a little bit different. So for an x value of -1, then our y value is 10 to the -1, or 1/10, or as a decimal will be 0.1. And so that's there at -1. And so it's just a very small number there, just above the x-axis at 0.1. But for an x value of 0, we have 10 to the power of 0, which is 1, just like it was here for 2 to the power of 0. And then we go here to an x value of 1, then our y value is 10 to the power of 1, which is 10. So that's that point there. For an x value of 2, we've got 10 to the 2, which is 100. So we can't fit that on the scale here, but we know it's way up the top, and you can imagine, 10 to the power of 3 would be 1000. And so very high up. And so if we kind of compare these two graphs here, y equals 2 to the power of x and y equals 10 to the power of x, they are similar in shape, where we can see that our y values sort of slowly increase to start with, but then once we get into positive values of x, it increases rapidly, and more so when our base here is a bigger number compared to this one here of 2. So let's look at some key things that are the same. Well, for this basic graph or function, y equals b to the power of x, with no other kind of parts on there, translations, transformations, and so on, just b to the power of x, our y-intercept, you'll notice, is exactly the same regardless of our base. That's because when our y value is 0, our x value is 0, our y value will always be 1. It's not going to be 1 when we introduce transformations, however, but for this basic graph, it will be always at 1. And a key easy point on there is always going to be when our x value is 1, our y value will be whatever our base is. Okay, because our x value of 1, our base is 2, then y will be 2 to the power of 1 or 2, and in this case 10 to the power of 1 or 10. Let's just have a look at the nature of the graph as we look at negative values of x. So the further we go negative, you'll notice that the graph is just continuing kind of almost horizontal, but it never actually goes on into negative values of y. Let's just have a look at what we've got. Let's take a very large negative value for x, say negative 100. So if we have an x value of negative 100, and we're looking at 2 to the power of negative 100, then that's the same as 1 over 2 to the power of positive 100. Now, 2 to the power of positive 100 itself is a very, very large number. But because it's in the denominator, 1 divided by that makes the whole number, it's the whole fraction here, as an extremely small value. It'll still be positive, but extremely small. Same as if it was 10 to the power of negative 100. Then that's the same as 1 over 10 to the power of positive 100. 10 to the 100, extremely large number. It's 10 followed by 100 zeros. Okay, but 1 over 10 to the power of 100 must then be an extremely small value. Virtually 0, but not actually 0. Still positive, but only very slightly. And so what that means is as our x values are just getting increasingly negative, our y value gets closer and closer to 0, but will never actually reach 0. That makes our x-axis something called an asymptote. Asymptote is spelled A-S-Y-M-P-T-O-T-E. An asymptote is simply a line, like an imaginary line, if you like, that a curve will approach but never actually touch. Okay, and so that's the situation here with these exponential functions. And so for each of these graphs of y equals b to the power of x, regardless of your base, okay, we're just considering base values which are greater than 1, then we're going to have this type of graph, okay, which going from negative through to positive. It starts off where our y values are growing slowly, but then it grows quite rapidly afterwards. Hence the term that we often refer to things when they grow quickly as being exponential growth. So they have these three things in common. The x-axis is the asymptote. Okay, the y-intercept will always be at 0, 1, and this point 1b is an easy point on the graph that we can find. Okay, so that's an introduction to exponential functions. Okay, and I'll do a follow-up video where we could look into some other examples. Okay.